Okay, so today we are going to discuss about the characteristic curves of a transistor. There are three characteristic curves. One is input characteristic curve, and then we have transfer characteristic curve and output characteristic curve. So we will discuss each of that. Okay, so you can write the topic as characteristic curves of a transistor. So write down the topic characteristic curves of a transistor. Okay, and then first topic, input characteristic curve. So input characteristic curve is simply we study the base current. Now, for example, the first topic is input characteristic curve. Here it is there. Input characteristics curve. So here I draw a transistor here. So for this, you can consider common base or common emitter configuration. It's totally fine. So here base, NPN. So here this potential difference VBE, that one you can control by putting a variable uh, battery here. Okay. With that, you measure the IB current. So for that, you have to put a microampere ammeter, microammeter. Okay. Okay, so here usually what you do is while changing this VBE, that by this changing this voltage, you measure this IB current. So this is actually a PN junction. So therefore you will get a characteristic curve very similar to PN junction. Okay, so here if it's a silicon transistor, so this is the shape that you will get, right? So input characteristic curve is the variation of IB versus VBE. So input current IB against input voltage VBE. How the input current varies with the input voltage. Okay. So this input characteristic curve, that is very similar to a PN junction or a diode. So input characteristic curve of a diode, right? Okay. Okay, so you can write this. You can the variation of input current IB against input voltage VBE is plotted in input characteristic curve. Okay, as BE junction acts as a normal PN junction. A PN junction we studied earlier, like in diodes. The input characteristic curve of a transistor is also similar to the page. The input characteristic curve of a transistor is also similar to the, it should be PN junction. Similar to the PN junction. You have right here PN junction. So the variation of input current IB against input voltage is plotted in input characteristic curve, and then you can draw this diagram. I mean the graph, the curve of IB versus VB. Always remember IB current is in microampere range. It's a very small current. Okay, and then after drawing this curve, you can write as BE junction acts as a normal PN junction. The input characteristic curve of a transistor is similar to the PN junction. Okay, and we know in a PN junction, if you have a silicon transistor, there will be considerable current if the voltage is higher than the barrier voltage. Now, for example, for silicon, barrier voltage is the potential barrier is 0.7 volt, right? So similarly, here also you can find if the NPN transistor or PNP transistor is made of silicon, then that particular value will be 0.7. Okay. So in transistor input characteristic curve, there is nothing much to learn. It's very similar to what you have studied in PN junction, because it's basically a PN junction, right? So E, right? If you consider an NPN transistor, so base is P type and N is N type, so it will be a PN junction. Okay. And write down the topic transfer characteristic curve. Transfer characteristic curve. Transfer characteristic curve. Okay, so here this current represents the variation between the input and the output currents of a transistor. So which are IB and IC. We consider IC as the output current and IB as the input current. Okay, so mostly when we are talking about this characteristic curve, the main configuration that we consider is common emitter configuration. So therefore, base IB current will be the input current, IC current will be the output current. Okay. So write down topic transfer characteristic curve. Guys, do you find my voice is lagging?
No, sir.
Okay, thank you. Okay, so write down under this curve represents the variation between input current and output current. So input current is IB and the output current is IC. Okay, so please draw this curve, draw this graph. After that, I will explain you. Once you're done with the drawing, raise your hand, or you can drop a message say done. Okay, okay, good. Akhil, are you finished drawing? Okay, good. So here we have the variation. Well, here we have the variation of output current versus the input current. So the output current is IC, which is in the range of milliampere. So the unit has taken as milliampere, and IB, as always we know, it's in the range of microampere. Okay. So now here in this graph, the first region is cutoff region. The cutoff region is that means in that region the transistor is not active. Okay. That means now, for example, okay, let me explain you with uh, transistor. I'll draw that. So I'll take a common emitter NPN transistor. So this emitter base, let's say I want to measure the current. So microampere, and then this is PN, has to be forward biased. And the correct, this one should be reverse biased. So this NPN. Okay, so NPN. Okay, so here we put a milliammeter to measure the current. So the had to mark the current. So always in this direction P to N. So this current is IE. Here the current is IB, and here the current will be IC. Okay, so here we know, now let's say here is a switch. Here is a switch, say, or else let's say I have, yeah, there is a switch. Okay. So there is a switch here. So switch is off. That means no current in this input circuit. So this is the we call input circuit. Input circuit is the output circuit. Okay, so here IB is considered as the input current. Okay, and then IC is considered as output current. So now suppose if this switch is open, that means this circuit is there is no current is running in this circuit, input circuit. That means this BE junction is not biased. So if BE is not biased, no matter how much you increase the voltage here, okay, there won't be any current in the output circuit, right? If you want to have a current in the output circuit, you should bias the BE junction. So how do you bias the BE junction? You have to increase the voltage by from 0 to 0.7. Now in the input characteristic curve uh, that you studied the variation of IB versus VBE. So when you increase the VBE, so the IB current is gradually it will be 0 until 0.7 and then it will increase. So here until you reach this 0 point barrier voltage, there won't be any current in the output circuit, right? Now if you want to get a current in the input circuit, you have to give a voltage that is VBE should be greater than 0.7 volt. Okay, then only this junction will be biased. If the BE junction biased only, you can find a current in the IC, in the output circuit. Okay, so if you want to bias that, then if you want to bias the BE junction, you want to give a voltage that is greater than 0.7. So in this range, you can see there is no current will be in the output circuit. So that's why it is known as cutoff region. Do you all understand? Any questions? Usman, did you understand? එතකොට මේ if the BE junction is not biased, there won't be any current in the output circuit. So that's why it is known as cutoff region. Okay. So after that, what happens? After that, after this value, if your BB is higher than, let's say you are fixing at 1.5 volt, you are keeping the VB 1.5 volt. So therefore, there will be a corresponding IBE value. Okay, so therefore there will be a corresponding IB value. Maybe that IB value something like it's in the micro ampere, right? So it could be something like 10 microampere, for example, let's say, right? 10 microamperes. That means there is a current passing through, so this is biased. So therefore there will be an output current. So therefore there will be a current in the output circuit. So we can call now the transistor is active, right? So if the VB is less than 0.7, the junction is not biased. Therefore, no matter how much you increase this voltage, there won't be a current in the output circuit. Therefore, it is known as cutoff region. But once the BE junction is biased, and there will be some value of IB current in the range of microamperes. So then the transistor will be active. It becomes active. Okay. So once it becomes active, now what we do is, okay, and then again you can increase this VBE or this voltage. Okay, then we increasing the voltage further, you can increase this IB current. Okay, can increase this IB current, and then what happens? It will gradually increases. IC current also gradually increases, right? Okay, so I'll explain this again. Okay, suppose the BE junction is not biased, means there won't be any current, so that there will be cutoff region. But the BE junction, let's say the voltage is increased more than 0.7 volt, then it becomes active, therefore there will be a considerable current in the IC, in the output circuit. Okay. And then if you're increasing this value further, that means you are increasing the IB current. When you are increasing the IB current, the IC current also increases because it will support, right? Uh, so when this junction becomes more biased, it will be more easier to transport for the mobile carriers, charge carriers, right? But when you're increasing further, and there will be a come to a limit, and then the IC current will be saturated. So by increasing further uh, at a maximum value, the IC current will be saturated. Okay, here as IB increase, initially there is no variation in IC. This is known as the cutoff region. The transistor doesn't work in cutoff region as there is no output current. This is also known as the switch off position of a bipolar junction transistor. Okay, so this is the biggest advantage of a transistor. Okay, now if you take normal switch, we can mechanically on and off. But if we take like a electronic uh, chip, we can't do that mechanically operate, right? Because moving mechanical parts, it occupy large space and all. That's why early days computers were very big. Okay, but now everything we can handle within inside the circuit, right? So here what we can do is, so by we can use this transistor as a switch. Okay, so if the BE, no matter how much you have voltages here, if you bias this only, there will be a current. So you can use this as a switch. If you bias this, there will be current. If you make this IB current 0, then there won't be any current in here. So it is the action, switch action of a transistor. Okay. In active region, IC and IB have a linear variation, and current gain equation alpha beta AI can also be applied. Also, transistor work as an amplifier in this region. So in this region and the active region, the transistor work as an amplifier. Okay. Okay, and in a common base configuration, we know there is no any considerable current gain, but in the common emitter configuration, there will be a significant current gain, and in the common collector configuration as well. Okay, after a certain IB value, IC will no longer increase and be constant. That is because it depends on this value. Uh, the maximum value is depend on this VCC, the supply here, this voltage. The maximum, this saturated I value, this maximum value, let's say I naught, or I is double dash. So that is depend on, I double dash depends on this value. Okay. So if you increase this further, you can increase this to I something like this. So that one is the next thing that we are going to see. Okay. The next characteristic curve. Okay. So in this transfer characteristic curve, we keep this value constant. This value has to be constant. Okay, because we study how IC changes with IB. Now, if you want to change the IB, you have to change this voltage. Okay, In a transfer characteristic curve, you study how IC changes with IB. And in order to change the IB, you have to change this voltage, no? Or else what you can do is you can keep here a larger voltage. You can apply some considerably large, I mean, not has to, cannot be very large voltage. It's a normal voltage, but comparatively large voltage, and you can put a large resistor. And while decreasing the resistance value, you can put a rheostat or a resistance box. By decreasing the uh, resistance value, you can increase the IB value. Okay, so something like that experimentally you can do. Okay, okay. So in transfer characteristic curve, you study how IC varies with IB. Okay, okay. Uh, is that uh, is it all clear, Sithira? Do you have any questions regarding this?
No, sir, no questions.
Okay. So here we keep this voltage constant. Okay. VCC, this voltage we keep constant. Now in the next one, output characteristic, what we are going to study is while changing the VCC, how IC will change. So that one we will see. Okay. So you have to put a note here. Let's write down the note. I think it's better if you can draw the circuit also, this circuit next to the curve, so that it will be easy for you. You will easy to illustrate. I mean, with this, you get some idea, right? So I think it's better you draw the circuit. Please draw the circuit. Okay, are you done drawing the circuit? Okay. What about Usman?
Yes, sir. Done.
Okay, thank you. So then we can write down. So write down initially there is no. Wait, we'll write down like this. uh, okay, so write down initially there is no variation of IC. Initially there is no variation of IC because BE junction is not biased. Because BE junction is not biased. BE junction is not biased. Initially, there is no variation of IC because the BE junction is not biased. So within bracket, you can write IB equals to 0 since IB equals 0. Okay, and IB equals 0. Right? Within brackets, you can write IB equals 0. And then next point, write when VBE is greater than 0.7 volt for a silicon transistor. For silicon transistor, when VB is greater than 0.7 volt, BE junction will be biased. BE junction will be biased. BE junction will be biased. Therefore, 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 uh, IC will vary linearly with IB. By the way, before this point, I want to say this. We wrote this right. Initially, there is no variation of IC because BE junction is not biased. So the IB in bracket we wrote IB equals to 0. There we had to mention this is known as cutoff region. In that point, this is known as the cutoff region. Okay. And the second point, you can start this. Okay, I read the sentences. First, initially there is no variation of IC because BE junction is not biased. Within brackets, IB equal to 0. This is known as the cutoff region. Okay. So now it is very clear, therefore the transistor doesn't work in cutoff region as there is no current. Okay. This is also known as the switch off position. Okay. This is also known as the switch off. Okay, and next point you can start when VB is greater than 0.7, BE junction will be biased and therefore IC current will be there or output current will be there. And this IC output current increases linearly with IB. This IC current increases linearly with IB. This region is known as active region. This region is known as active region. Okay. This region is known as active region. And then last point you can write after a certain IB value, IC will no longer increase and be constant. This is known as the saturated or switch on state of a BJT. That means bipolar junction transistor. So this is switch off This is switch on. Now if you want to use as amplifier, that you use in active region. Signal amplifier we use in active region. So these regions we use for switch, transistor as switch. So this region we use as transistor as a amplifier. Okay. So here also we will mention during the transfer characteristic curve, VCC value keeps constant. Okay. You can say VCC or sometimes VCE, the collector emitter, voltage across collector emitter terminal. Okay, either one you can write, it's totally fine. In some textbook they write VCC, some textbook they write VCE. So it's totally okay. So here in this entire process we keep VCC constant. Okay. Okay. So that is about transfer characteristic curve. So in transfer characteristic curve, we keep this value constant and we study the variation of IC versus IB. Okay. And the last one, output characteristic curve. Okay, so right on the topic, output characteristic curve. So the variation of the output current IC against output voltage VCE is plotted in output characteristic curve. IC varies with VC at different values of IB. Therefore, three variations plotted in this graph. So there are three variations. One is IC, IB, and VCE. I'll explain you first. Draw this graph. Yeah, this part of the graph should look like more like straight line. Okay, something like this. And then now you draw a straight line. And then it's not turning like this. It has to be a curved shape. Okay. Turns like this. Okay. So here IB equals 0, IB 20 microampere, 40 microampere, 60, 80, 100 microampere. Okay, so here we can note this. Now here IB equals 0. IB equals 0 means BE junction is not biased. So when the BE junction is not biased, it doesn't matter how much you increase the VC value, IC value remains 0, right? So if the BE junction is not biased, no matter how much you increase the voltage in the output circuit, there won't be a current, okay? So therefore it is known as the cutoff region, right? That is similar to what we, in the previous graph, we mark the cutoff region now, because that in that cutoff region, the BE junction is not biased, right? Okay. So did you all understand that how this IC is 0? Akhil, did you understand? Okay, good. So, and then that is cutoff region. So if IB is 0, that means B junction is not biased, then no matter how much you increase the VCE value, IC remains 0. But there is a small leak current is there, but it is again very small, negligibly 0, okay? Okay, and then this is saturated. Now, for example, let's say 20 microampere, IB is 20, okay? And if the VC is very small, okay, I'll draw this graph and I'll explain you with that. Everything's connected. You have to understand very well. So here I'm going to draw the transfer characteristic curve. So transfer characteristic curve IC versus IB. It will be like in a straight line saturated. So I is saturated. Okay, the cutoff region. After this saturated and this active region. Now, if VC is very small, like here, okay, let's say for example, I consider IB is 20 microampere, IB 20 microampere, okay, IB is 20 microampere, okay, and VCE, let's say very small, VCE very small, so for 20 ampere, very small value, VCE. That means it quickly saturates, because now let's say this is VC for example, let's say this is for VCE is something like let's say 20 watts volt, 10 watt, okay. Suppose if I keep VCE small, something like 2 volt, okay, then the current will saturate it very soon, okay. So therefore here, if the VC is small, the current will quickly saturate, right? It will saturate. The VC is small. If you want to have a good active region, you have to have a large VCE value. So you can increase the IC along with IB after reaching a large value, and then it will saturate. Okay, this one little bit difficult to understand, but I hope got some idea about it. Okay, let me know whether you understood. I need a response from each of you.
Understood.
How about Usman?
Got it, sir.
Okay. Akib? Okay, I'll explain it again. Okay, suppose let's say VC is 10 volt. So when you increasing the IB, IC also increases and increase, and it becomes saturated. So here it will be saturated. Okay, saturated. But if you have a lower VC value, something like 2 volt, or let's say 1 volt, even smaller value, 1 volt, then what happens as you increase the output circuit battery has only small, can generate small current, so all the current will be saturated. So no matter how much you increase the IB, this one will reach to a maximum value, so it will be saturated very soon. So you can see if the, now here in this graph VCE, so here this region means the VC is very small value. Okay, now for example here for 20 microampere, this one could be something around, VC is something around let's say uh, 1 volt. So even in 1 volt the current is saturated, maybe something like 0.5 volt. Okay, so when IB is 20 microampere, and if VCE is 0.5 volts, the current will saturates. Okay, now here, now you have to understand with this graph. Now here how it increases. Now if the IB current is not there, and that means in cutoff region there is no IC current, and after biasing bias the BE junction, then there will be a IC current that increases linearly with the IB. Okay, it increases linearly with IB. If you increase IB more and more, IC will increases, and then there will be maximum, because it's like this. Okay, so now here uh, so now if you take the transistor, I draw a rough sketch. Okay, so here this VCC. Okay, and this transistor. So this will, what is this doing? It is uh, giving some current, right? Now the battery EMF, electromotive force, is it pushes the charges with some force. That is what we call electromotive force. Now for example, it pushes some let's say 100 volts, for example. Let's say instead of current, let's say 100 volts, or else it pushes water. For example, it pushes water in this side with large quantity. But now here is, there is a tap. So if you open this tap only, this will can come. Okay. So here again, this. So Now this battery, it pushes the charges with some rate. Let's say it will pushes some current, okay? And then here we have BE junction. It's like a gate, okay? Like a tap. For example, you can think like this. Okay, normally what you can think is, okay, I'll explain like this. Now from the water pump in your region, it pushes the water with some pressure. It comes with larger pressure. But කොච්චර high pump කරත් වැඩක් නැහැ වා tap එක ඇරියෙ නැත්තම්, right? So when you open the tap small, the current will come, water will flow slow. If you increase the tap more, it will, the rate of water dripping from your tap will increase with the amount of your opening, no? And after that, once uh, the rate, I mean, let's say it pushes with the rate of 20 or 1 liter per second, or not 1 liter now. For example, think the pump, they are pumping with some rate, okay? It pushes with a large rate, but if you close the tap, the water doesn't come. But if you open little, it will flow little, okay? And if you increase more, that means you are increasing the IB current. If you increase the IB current, IC also increase. And then මේ tap එක ඇරලා යනකොට IB එකත් මොකද IB එකත් එක්ක IC එක වැඩි වෙනවා. The IC current will increase with IB. And after that, what happens, this comes with the maximum speed. Once that maximum speed is reached, ඊට පස්සේ කොච්චරක් open කරත් ඒ rate එකෙන්ම එන්නේ. It will come with the same rate, with that maximum rate. Do you understand?
Yes, sir.
Okay. So now with that we can say, now if VC is very small, you can see if the VC is very small, it's very small, the current is saturated. But in order to have active current, you have to have a large VCE value. Okay, understood? So then it will be active here. So these are active region. These are active region. These saturates. These saturates quickly because the VC is not enough to have an active operation. Okay. Okay, so this is the output characteristic curve. Okay, do you have any questions regarding this now? Okay, so then let's move on. Okay, so use of a transistor. So we are going to discuss two applications, one as a switch, one as an amplifier. Okay, there are two main uses of transistor. One is as a switch, the other one is as an amplifier, signal amplifier. So write down this part. Okay, and then write down the first topic, a transistor as a switch. A transistor as a switch. Okay, so transistor as a switch is very simple. If the BE junction is not biased, it's switch off. If the BE junction is biased, then switch on. That is the basic underlying principle in a transistor as a switch. Okay, so here when RB is at a greater value, so if the RB is very large, then this current will be very small. IB becomes very low and transfer will stay at cutoff region. Therefore, IC is equals to 0 and bulb will not glow. This is switch off position. Okay, so here IC is 0. Okay, so there is no current here. Therefore, VCC is equals to VCE. That means the voltage across CE junction is equals to the VCC. By decreasing the value of RB, IC can be increased and the transistor can be brought to saturated region. The maximum current will flow through the collector at this position. This is called switch on position. So when switch on, VC is approximately 0. Actually, it is 0.1 VCE. VCE is equals to 0.1. So we can consider it is approximately equal to 0. So when a transistor saturates, always VC is uh, equals to VC is equals to 0.1 or approximately 0. Okay. So all you have to do is draw this circuit and write this down. If you have any questions, you can ask. VC equals 0.1 volt and that's VC is approximately equal to 0 volt. Let me know once you're done writing.
Okay, sir.
Okay, and then transistor as an amplifier. Write down the topic, transistor as an amplifier. Okay, transistor mainly used as amplifiers. An amplifier can amplify, increase the amplitude of a voltage or current signal. Okay. An amplifier can amplify, increase amplitude or voltage of current signal. These transistor amplifiers are mostly used to amplify a sound signal or radio or sound setup. Other than that, there are many transistor amplifier applications which are used to amplify a small signal to a signal with higher amplitudes. Okay, so write down an amplifier means. So you should know what is the amplifier means. It's a amplifier means it increases the amplitude of a voltage or current signal. Okay, so mostly we use the common emitter uh, transistor as amplifier because we studied already in common emitter. It can give large current gain and voltage gain as well as the power gain. Okay, so write down subtopic common emitter transistor amplifier. In the above, here you can only write these two highlighted sentences, that's enough. And then after that, write the topic common emitter transistor amplifier. Okay, so common emitter transistor amplifier is considered as one of the best amplifiers as it has a good current amplification as well as voltage amplification. Input signal is given to the base and the output signal is recovered through the collector. So input signal is given to the base and the output signal received through the collector. That one you should have already understood because common emitter means the input circuit is base, output circuit is collector, right? You can't take base as the output circuit because base has the small current and collector will have the large current. Okay, the transistor is biased to in the active region. So in the active region throughout the whole process. In amplification, it has to be in active region. Okay, the transistor is biased to in the active region. Highlight in active region. Okay, throughout the whole process. Input voltage signal is given through a capacitor as well as the amplified output voltage signal is received through another capacitor. This is to make sure that the base current and the collector current do not leak out to input or output circuits, as that can change the biasing of the transistor. So here we want only to amplify the signal. We have to take some input signal and we can want to take amplify it, right? So we don't want the base current interfere with the input or collector current interfere with the output signal. So therefore here we have to put uh, capacitors. Okay. So write down this one also. Input voltage signal is given through a capacitor, as well as the amplified output voltage signal is received through another capacitor. This is to make sure that the base current and the collector current do not leak out to input or output circuit. That base current and collector current, which is input and output current, should not leak to input signal and output signal. That's all. Okay, as that can change the biasing of the transistor. So that entire thing you should write. Okay, so always remember, in transistor as a switch, off means the B junction is not biased, cutoff region. Switch is on means it's fully biased and then saturated. In amplifier, we use the wall process as in the active region. Okay. Because now let's say after a certain value of the input signal, now input signal, let's say current increasing. So when increasing, IB also increases, and this, let's say this input, look at my hands. Okay, this is input, this is the amplified signal. Okay, so if the input is, oh no, sorry, this is the IC current. Okay, if this input as sine wave, it's increasing, this is also increasing. So this increasing, but this saturated, this still increasing, it's saturated. So it is a kind of a disturbance, right? So it won't give the exact variation. We want to get the frequency should not change, right? And also the same variation should be there, only we want to amplify. Therefore the entire process should be within the active region, because in the within the active region, IB is proportional to IC is proportional to IB. Okay. So here can common emitter transistor amplifier. This output signal is taken from here, and then input signal given from here. Okay, so transistor is biased in the working condition so that VBE must be greater than 0.7 volt. So VBE we bias to some value, let's say 1 volt. Okay, so it is biased. So B junction is biased. Okay, so and then the input voltage is given. So input voltage, it's a signal in this. Okay, so here already have some voltage, let's say 1 volt, and then input voltage is oscillating here. Okay, so if it's now, let's say this at 1 volt, and then input signal has amplitude of like 0.2 volt, then this will oscillate 1.2, 0.8, 1.2, 0.8, 1.2, 0.8, like that. Okay, so here this voltage, and then this the input voltage. So if we add these two, so this addition is very similar to wave superposition. Just you have to add the two waves, okay, amplitudes. Okay. So this is the input voltage and input characteristic curve. Okay, so input characteristic curve. So here VBE value. So this value is changing. So that is here IB, how IB changes. IB current changes. That's not the output. Okay, and with this IB, IC will oscillate, right? And we know if it is the transistor in the active region, IC is proportional to IB. So that one I think the next page here. So here now with the IB, IC varies. Now here IB corresponds to this value. So you can see throughout the process, it has to be in the active region. So this is very important. So here this is cutoff region, right? To here cutoff region. This is cutoff region, and from here to here it will be active region and the saturated. So amplification process should occur within the active region. Suppose let's say this value, suppose this comes to here, then it will be a disaster. We can't amplify as we wanted. Do you all understand? Usman Tevnada?
Yes, sir.
Okay. So within the entire process, the transistor should be in the active region. Okay, I think you need to draw this. Okay, starting from this. Or else you can take a screenshot and you can draw complete all this. I'll give you 3 minutes. Draw as much as you possible, and then make sure first you take a screenshot. මම මේක අදින්ට කියන්නේ දැන් මේවා මේ ටික ඔළුවට දාගන්න ඕනේ while you refer, right? While you write. මේ electronics එක හරියටම තේරුම් ගත්තා නම් it's very easy. You can even explain someone. If you explain someone, it will be, you become expertise in that lesson, in that session. And once we're done with this transistor, we'll do past paper questions related to transistor part. Maybe tomorrow paper class, we will do more on questions focusing on transistors. Okay, you have school, right? So this input voltage is very small. It's like millivolts, right? So here you can see if it's 1 volt, this is oscillating like 1.2, 0.8, 1.2, 0.8, something like that. And it's sinusoidal. Okay, so you can take a screenshot, complete this whole thing. Everything should be there in your writing book. So here this how VBE varies with So IB varies with VBE. Okay. So this is the variation of input voltage. So this with the VBE value, the IB variation of IB current, base current. And we know in active region, IC is proportional to IB. So you can see here, this value corresponds to this. And it's increasing like this, so IC increases. So along with this, IC also changes. Okay. So now you can see when IB increasing, IC also increasing. Therefore, there is no any phase change. Transfer characteristic curve is used to get the variation of output current IC with time t using the variation of input current IB with time. Okay, so this both here IB, how it varies with time, IC varies with time. There is no phase difference between IB and IC, right? Okay, because we are using this common emitter configuration, we studied that in common emitter configuration, there is no phase change. As input current is in microamperes and the output current is in milliamperes, this graph denotes that there is a current amplification. So it is very clear that current is amplified. Okay. By applying Kirchhoff's law, VCC equals VCE plus ICRC. Okay, I want to here. VCC, this voltage, is equals to ICRC, this voltage difference plus this voltage difference. Okay. As VCC and RC are constant, V out and IC have inverse proportions. Okay, because it's minus, right? IC minus IC. So if IC increases, V out decreases. Output signal is amplified, but input and output signal have 180 phase difference. Okay, so there is no phase difference between the current, but there is a phase difference between input and output signals. So this is the input current, how it varies, this output. Since we are taking this as the output. Okay. Now, when we study the common emitter configuration, we consider the output as the load resistor. So in that case, there is no phase change. But now here we are taking this as the output. So thus there is a phase change. Loading. Okay, so here in common base there is no phase change, right? And common collector, I think this common collector is wrong. And common emitter, there is a phase change, right? Because you can see if I draw this here, the current passing through resistors are in two different directions. So there is a clearly a phase change. Okay. So you need to draw these input output, these graphs as well, transfer characteristic curve. So here the entire amplify process is within the active region. So this is the case. What happens if the transistor goes beyond if it's got saturated when amplifying? So you can see some part of the current is signal is what do you call? We can call it as noise. Okay. So there will be small noise. The signal is disturbed. Okay. Now if I'm using a for example, I have a mobile phone, one connecting to speaker, loudspeaker. So if that thing happens, what happens here at these occasions, the sound is not clear, right? The sound will be disturbed. We call it as noise, right? Okay. Okay, so this is not in the syllabus, I think. DC load line. Variation of the collector current with the collector emitter voltage for common emitter transistor configuration is known as DC load line. Variation of the collector current IC with the collector emitter voltage VCE. Okay, so see, says this output characteristic curve we can take as the DC load line. VCC equals ICRC plus VCE equals quiescent point, Q point, operating point of a transistor. A transistor can be biased to work at any point on the DC load line. These points of operation are known as quiescent points. Q point is decided according to the function of a transistor and bias accordingly. Okay, but this point only you should know. Transistor amplification is good when VC is equals to VCC divided by 2. Only this fact you should know. Okay. You won't be asked any question about this graph or quiescent point. Okay. But a transistor work well when VC is equals to VCC divided by 2. This fact you should know. Okay. So then with that we are done with BJT, bipolar junction transistor, and then we have field effect transistors, field effect transistors, effect junction field effect transistor. So N channel JFET and P channel JFET. So this one I will leave to our next class discussion. Yeah. because I can't do it fast. So now the remaining another 20 minutes are there. We'll do some past paper questions related to transistor. Okay. If you have any already, if you have some questions, you can share it to me. Okay, I'll find some questions.
So shall we do essay question?
Yeah, essay
Okay.
questions. I mean the essay questions, yes. If you have some question, you can send it to me. It's fine. I might have some past papers. Okay. So 2017 paper. Let's discuss this. First, I can give you some few minutes to carry on the question. So please start this question. I'll have some water. Okay. Write down the expression for the relationship among IC, IE, and IB of an NPN transistor or symbol have their usual meaning. It can be either NPN or PNP, whatever the transistor, it always IE equals to IB plus IC. The NPN transistor connected as shown in figure 1 is operating in the active mode. Okay, so it's in the active mode. So BE junction is biased. Okay, assume that the current gain of the transistor is 100. So, so this in common. Common emitter. So common emitter configuration. So current gain is 100. That means beta equals to 100. Beta equals 100. And when it is forward biased, the voltage across the base and the emitter is 0.7 volt. Okay, so it can be a silicon transistor. So here this B junction is 0.7 volt. Problem number 1. Calculate the base current IB necessary to produce a collector voltage of 5 volt. Collector voltage of 5 volt. So here this voltage, calculate the base current IB necessary to produce the collector voltage of 5 volt. Okay. So here this voltage has to be 5 volt. Okay. And this is 10. Therefore, IC I can find. I can find IC. Okay. So we can use Ohm's law. V equals IR. Okay, so here we want to find IC first. For that I can use V equals IR. So this is 5 volt. So voltage across this resistor, 10 kilo ohm resistor, using Ohm's law. So since essay paper, you had write this, okay? Using Ohm's law for 10 kilo ohm. So therefore, V equals voltage is 10 minus 5. The voltage difference is 5 volt. 10 minus 5 equals IC times R is 10 kilo ohm. So therefore, IC equals this 5 divided by 10 is 0.5. Kilo comes to the other side, it becomes milliampere. So IC is 0.5 milliampere. Therefore, beta is equals to IC over IB, right? The current gain beta equals IC over IB. So 100 equals IC over IB. Therefore, IB equals to IC divided by 100. So 0.5 milliampere divided by 100. So we get 0.005 milliampere. Or else I write in. So 0.5 divided by 10 to the power minus 3 and 10 to the power minus 5 ampere. So this equals to 5 microampere. So IB is 5 microamperes. Calculate the base current necessary to produce the collector voltage of 5 volt. So that is 5 microampere. Okay, calculate the value of R2. Yeah, R2. If R1 is 12 kilo ohm, assume IB is negligible for this calculation. Okay. So Roman number 2. Calculate the value of R2 if R1 is 12 kilo ohm. Okay. So this is 12 kilo ohm. Okay. Assume IB is negligible for this calculation. Okay. Calculate the value of R2. We want to find R2 and this R1. So here we can write this is 12 and this is 0.7 volt. Calculate the value of R2. R1 is 12. Yeah. So here we can write 10 volt divided by R1 plus R2 is equals to 0.7 divided by 0.7 divided by R2 potential divider circuit, because the IB current is negligible, so we can consider this as a series of resistors. Here the potential at anyway has to be 0.7 volts. Okay. So then here we can write, we want to find the value of R2. We can do cross multiplication. 10 R2 equals 0.7 R1 plus 0.7 R2. So we can take this to the other side. So 10 minus 0.7 is 9.3 R2 equals to 0.7 into R1 is 12 kilo ohm. So 12. So here R2 therefore 0.7 multiplied by 12 divided by 9.3 kilo ohm. There 0.7 into 12 divided by 9.3. 0.903. 2 is, so I can write 903 ohms. So 0.903 kilo 10 to the power 3, so multiply by 10 to the power 3 with 903.2. Ten divided by R1 plus R2 equals to 0.7 divided by 0.7 divided by R2. And then if you do the cross multiplication, 10 R2 equals 0.7 R1 plus 0.7 R2. Take the other side, 0.3. Yes, 0.7 R1 is 12 kilo ohm. The unit of kilo ohm here. So yeah, R2 is 903 ohms. Okay, and then modify the given circuit shown in figure 1 so that it could be operated with a negative power supply voltage of minus 10 volt. Correctly re-label the modified circuit using R1, R2, 10 kilo ohm and labels A, B given for the points in the appropriate manner. Indicate the direction of the collector current and the direction of the current through R1, R2 with arrows. Modify the given circuit shown in figure 1 so that it could be operated with negative power supply voltage, okay, of minus 10 volt. Correctly relabel the modified circuit using R1, R2, 10 kilo ohm and the labels A and B and the labels A and B given for the points in the appropriate manner. Indicate the direction of the collector current and the direction of the current through R1, R2 with, okay. So here we want to now replace this, okay. So this is 0 and this is 10. So the difference is plus 10, okay. Now we want to modify this with minus 10 voltage, okay. So if I make it as minus 10, okay, so it's like this. Now relative to this point, okay, so I, yeah, let's say this point is P and this point is Q. So VPQ, the potential at P, VQP, VQP is equals to the potential at Q relative to P is 10 volt. Then what is VPQ? The potential at P relative to Q is minus 10 volt. So what you have to do is you have to draw the circuit upside down. It's the best thing we can do. Yeah. So wait. VQP is 10. So that means this is. So if I make this grounded, so this will be minus 10. Something like that. Minus 10 volt. Potential P related Q is minus 10. So now I want to make this minus 10 and then want to modify the circuit. My intuition says I just need to upside down the circuit, and here it's minus 10, and then this will come 10 kilo ohm will come here, R1 and R2 should change. And that's what my intuition says. Wait, it's logically the answer. Okay, so if this minus, okay, if this minus 10 volt, now we'll do logical reasoning. So this junction has to be this NPN. So this one has to be PNP transistor. Then this becomes minus, and this has to be a PNP transistor, isn't it? No, yeah. So I will draw this circuit. So this minus 10 volt line, and then I take this here, and this will be the emitter, base, collector, and then 10 kilo ohm should be here. And this should be grounded. And then this one should be R2, and this is R1, and point A remains the same. B point comes here. Okay, so and then IC, IE emitter is IE this side. So the collector should be this way, C and IB. So this is the circuit I think they're expecting to drop. Don't know whether this one has a marking scheme. Mm, 2017, no, this paper, 2017. See whether we have a 2017 marking scheme. 2017 marking scheme is not there. My God. minus 10 B R2 R1 and the direction BN, yeah, 10 kilo ohm IC direction this side, grounded here. Okay. So it's correct. So here what I basically did was just consider the polarity and I change the circuit accordingly. Okay, so I'll explain you what I did here. So this point is, let's say, Q and this is P. So VQP, the potential at Q related to P is 10 volt. That means potential at P related to Q has to be minus, the potential at P related to Q is minus 10 volt. Okay, so potential at P related to Q is minus 10 volt. So now I want to replace with minus now. So I take here minus. Now this is very similar. Here taking minus and this is 0 because here VPQ, the potential at P related to Q is minus 10. So that means this side I have to ground and here I have to give minus 10 volt. So I did that and what do I do? I take the mirror image of the circuit. Understood? So method minus 10 and here it should be grounded. And then we have to take the mirror image. So this will become okay, I can explain again. So VPQ is minus 10. Okay, here the potential is minus 10. Now we want to give a minus 10 volt. So I want to give 10 volt means here already minus 10 volt. When we grounded here. So if I grounded here and giving minus 10 here, so nothing different, same thing. And then I have changed the, so here this one is connected to the grounded. So accordingly I can change. Okay, so here this is, I want to take as minus, that I draw here, this is this part, and then from this I draw this part, and then this one is there and that is there, and this one, and then 10 kilo ohm, then 10 kilo ohm, and then it should connected to grounded, because if I consider 0 here, then this one will be minus 10. That means now, for example, if I consider this xy, the y is the Vyx, the potential at y relative to x is 10. Okay, 10 watts. I hope you have understood. Let me know if you have understood what I have done here. Let me start with Akhil. Akhil, did you understand? And Sithira? Usman?
Yes, understood.
Understood, sir.
Okay. And the C part, a photodiode is to be connected across the base and the emitter of the transistor in the modified circuit that you have drawn under B2. Okay. So in this circuit, A photodiode is to be connected across the base and the emitter of the transistor in the modified circuit that you have drawn under B3. When connecting a photodiode to a circuit, it is done in such a way that the photodiode is reverse bias. We know the photodiode works in reverse bias, okay, but the LED, light emitting diode, is forward biased, okay. Using the circuit symbol of the photodiode show how you would connect it correctly across the base and the emitter of the transistor in the modified circuit. When connecting a photodiode to a circuit, it is done such a way that it should be reverse bias. Using the circuit symbol of photodiode show how you would connect it correctly across the base and the emitter of the transistor in the modified circuit. Okay. So what we can do, so we have to use a photodiode. Photodiode works in the reverse bias. So, and you should remember the circuit symbol for photodiode. So diode is like this, and photodiode means the arrows inward, light emitting arrows outward. Okay, so this is the photodiode. So this one should connect where connecting photodiode such way that the photodiode is reverse biased. Using the circuit symbol of the photodiode show how you would connect it correctly across the base and the emitter of the transistor. Base and the emitter of the transistor in the modified circuit. Okay, so let's identify what is base. So this is base and this emitter. How would you how to connect? So this emitter. I think something like this. I'm not sure this. So this is N, this is P. So P should come this side, and then here connect here. I think it's like this. I'm not sure. Let's check the. Yeah, it's correct. Yeah, so what I've done is correct because it's I drew it parallel to this emitter base. Okay, so this one also again marked parallel to. So okay, I'll explain. So the terminals are, they are saying base and emitter. So emitter is connected here. Okay. So the emitter terminal is connected to this entire part, and then this is base. So considering these two, I connect this photodiode, and also you have to consider the polarity because it has to be in reverse bias. So P side has to get the negative. So this negative and this is positive, right? So this side should be P and this side should be N. Okay. If you draw this in the other way side, then it's wrong. If you draw like this, it will be wrong because you have to give the reverse bias. when the photodiode is connected to the modified circuit correctly, will it alter the resistance across the base and the emitter appreciably? Will it alter the resistance across the base and the emitter appreciably? Base and emitter. Okay. So, would you now this is will it there be a current base and emitter? Okay, so the potential difference across base and the emitter is only 0.7 volts, right? So therefore, even if it's a, let's say that is because it's a BE junction, the potential difference is 0.7. So therefore, that 0.7 is quietly enough to bias this, maybe or something like that. In fact, this is a reverse bias. So reverse bias means zero current. No, only little leak current will be there. So there is no significance change, right? Therefore, when the photodiode connected to modified circuit, will it alter the resistance across the base and the emitter appreciably? No. The reason is the BE junction, the one thing you can say, the potential difference across the diode is 0.7 volt. It's actually minus 0.7 volt, and also it doesn't give any current. Okay, because we know in reverse bias there is no any current passing through the diode. Okay, I expect similar explanation method. No. So the ප්‍රකාශ දියෝඩය සම්බන්ධ කරත්තේ පසු නැංගුරු ආකාරයෙන් එහි ප්‍රතිරෝධය yeah, since it's reverse bias, no current will be there. Okay, so therefore it won't change the resistance. Okay, when a rectangular light pulse of short duration is incident on photodiode, show the direction of the current through the photodiode in the circuit using an arrow. Okay. Show the direction of the current through the photodiode in the direction in an arrow. So when light is incident on it, it will generate some electron hole pairs. So it will have some small current in the direction. So this is minus 10 and this plus. Currents always move from large potential to low potential. For yes, we have a battery, current flow in this direction, so plus to minus. So therefore, if in case if generate some currents, so it will be in this direction, upward. Yeah, so the current will be in upward. Okay, and then draw the waveform of the voltage pulse appearing at the base relative to emitter and the waveform of the voltage pulse at the collector relative to the earth due to the light pulse at appropriate phase on the circuit. Draw the waveform of the voltage pulse appearing at the base relative to emitter. Base relative to emitter. Okay, so rectangular light pulse is incident on this. So then rectangular current is produced in the base IB. Okay, so will it there phase change? Yeah, because it's going upward, but the base is always towards this. So here it has to be a phase change, something like this. The waveform of the voltage, because normally when they say square, it is like this, right? So I consider phase change, so it has to be downward. Okay, so and the waveform of the voltage pulse at the collector relative to the earth due to light pulse. Okay, so collector, so we can see there is a phase change, the direction of the currents in base in collector. So therefore this has another phase change. Okay, so let me check my answers. So there are two ways you can draw the circuit, either this way or this way. So I will have to check which is one which I drew. And two. Yeah, at the base it has 5 phase change, and then the collector again another phase change. Yeah. Okay, I'll tell you how I identified these phase changes. So here the current is moving upward. Okay, current is moving upward. So you can consider including these two loops. If you consider these two in loop, then these two current with one loop, then it is both going in two different directions. So therefore there is a 5 phase change. And now IB and IC if we consider, then again there is a phase change. But suppose IC is in this direction, if in case, then IB and IC have the same waveform like this. Okay. Okay. So with this, let's conclude the today's class, and tomorrow also we will do more on transistor questions. So it will thorough your knowledge on transistor, because if you get transistor questions, it will be easy, right? Because here, in fact, here also there is nothing like complicated questions. If you studied, practice these questions earlier, then it is very easy. Okay, guys, sorry if I took so long. Good night. If you have any questions, you can ask. Okay, then. So, good night. Take care. Study well. Fi aman Allah.